used to show how magnetic fields work are based upon X's and O's, and this isn't like a discussion of football, it's X's, this means X's and O's, this is not football, okay? So here's the easiest way to remember this, okay? This is how I remember it anyway. So if anybody seen Pirates of the Caribbean, or familiar with pirate lore, right? What does X mark? Where the treasure is. What do you do at the X? You dig into it, right? So X's, when you see X's, that means the magnetic field is going into the page. Okay? It's the easiest way to remember. X's move in. O's, it's like you're looking into the hole and it's coming out. So let me give you a simple example. So, and part of this is that you have to be able to think like three-dimensional. So what I'm going to do is I'm going to give you a wire, and I'm going to give you the direction of the current being like this. Okay? So here's, when you see this diagram, so imagine that this wire is embedded in the page. So you see this on a page in your book. Here's the wire. It's in the page of the book. So to figure out the direction of the magnetic field associated with that current, you got this. You take your right hand and you point that thumb in the direction that that current is moving. Okay? So I put my right hand like this. So on the top, are you going to have O's or X? Gone!
Can we move on to
Yeah.
Throw the phone against the wall.
I was expecting that.
I do? He's getting married?
Okay, I'm over. I'm
What?
Go on, you're leaving.
Oh.
Watch the end of the video or get the last assignment from Jane Phillips. Okay, so if the current's going this way, what are you going to have on top? X's or O's? O's, why? It's coming out of the page. So on the top, you're going to put O's, right? Where are you going to have the most intense grouping of circles? Closer to the wire or further away? Closer, because there's an inverse relationship, right? So if I've got dots on the top, what am I going to have on the bottom? Have X's, okay? So down here, I'm going to put X's, okay? Got that one? Sure. Now, if I reverse it, and I put the current in the opposite direction, then I'm going to do the same thing. I'm going to take my thumb, I'm going to point it in this direction. On the top, I'm going to have X's. The bottom, I'm going to have O's. Go like this, okay? Cool, got that.
Do your assignments now?
Is it anyway okay?
Yeah.
Oh, this is just the first right-hand rule. There's more, okay? So this is why it's cool, like when we get to this test, and I watch you all taking the test, it's like watching gymnastics, because y'all were doing this and the wires.
Wait, are there?
That's-
Wait,
Oh.
wait.
What?
O's on the bottom?
That has nothing to do.
Yeah, so with this one, yeah, this is.
Okay, well, it
Oh,
looks
I'm
like
sorry.
It looks like an O on the left. Yeah.
Yeah, those are
I
all
mean an
O's.
X. Okay.
My pen is horrible. Yeah,
Okay.
yeah, they're O's. Now, a little bit weirder. See, here's the end of the wire, and there's going to be an X. Okay? Now, this is where you have to think like three dimensions. What I'm saying is that the wire you're looking at, like imagine that you take the wire and you cut it in half. So the wire is like coming out of the page like this. But there's an X. So which direction is the current? If this is the wire, is the current going into the page or out of the page? In or out? In. So, now, here is my wire. The current's going into the page, right? So which direction do I write my hand? Clockwise or counterclockwise? Clockwise. So in this situation, the magnetic field is going to be coming around like this. Okay? Now, if you put a dot, then what do you have? Then the current's coming into the page or out of the page? Out. So now it's going to be going like this. The current's going to be going in the counterclockwise direction. Around like this. Okay? So that's why you kind of have to be able to visualize it and go, okay, which direction is this thing going? All right? Right hand rule. There's going to be more. This is just the simple right hand rule of currents. And thankfully, kids always ask us, like, what happens if you have a kid that doesn't have a right hand? I was like, never had that problem. And hopefully I never do. Okay?
Well, sounds like
Sorry.
a challenge to me.
This could be terrible. So you just have to like go the opposite way the current's going. That's all.
Change it to the
Go with the
left.
electrons.
Just do the left hand rule, but opposite.
Like if it's going this way, then you can group on it.
What if he has no hand? Turn your left hand inside out.
Yeah, then he's just gonna have to use the right hand foot rule.
Push right. Wrap your toes right in the wire. You don't have a thumb on your foot, guys.
You have a big toe though.
That's a thumb.
Sideways.
Now, this is where it gets a little bit weird. So now I'm going to have a
I'm getting
loop
nostalgic for
with
this.
the current going around in a loop. Current's going around in a loop. Where's my X's? Where's my O's?
O's are on the inside. O's are on the inside. Yeah.
So the current's going this way. Current's going around in this direction. Okay, so here's my wire. The current's going around like this. So the current's going like this, so what's going to be in the middle?
O's.
O's. So I'm going to have O's in the middle. On the outside, I'm going to have
X's.
X's. Where do you think the magnetic field is going to be most intense? Inside or outside?
Inside.
Yes, it's a much smaller area.
We have to crush
If you reverse the current and make it go in the opposite direction,
Opposite.
yeah, so this gets a little bit weirder, so it's almost like gymnastics. So now you gotta wrap your thumb like this, and then it's gonna be going, actually, I screwed that up.
It's literally just going in a circle. It's not.
It's going around like this. So now, if the current's going in this direction, then it's gonna go like this, then you would have O's on the,
Outside.
and X's on the,
Inside.
So alternating current, oddly enough, alternating current goes back and forth. So what do you think happens with the magnetic field? It's constantly changing, okay? So you're always going from X's to O's, X's to O's.
You just need to make your
Now,
one direction to go.
here's the only mathematical formula for today.
The thumb is going up.
Exactly.
So then how is it the other way?
O's on the outside. Look, it's on the outside.
Wait,
Inside or outside.
what are you talking
Just bend
about?
your
What?
fingers backwards. It's not that hard.
That doesn't make any sense. Look, yeah.
So you have the ring.
Yes.
You grab the outside of the ring to make your thumb go up, right? Your fingers go on the inside.
See, you just
Make your
do
thumb go up on
this.
the other side. You have to grab through the inside of the ring. Yeah. So your hands will go around the outside.
Go like this.
So O's on the outside.
Just go like this like a normal person.
No. Why would I want to do that?
Oh wait, right, you're ginger. He's weird.
I'm sick of this.
Can we go back to like,
Wrong tism.
actually, can we just go back to when we didn't have this class?
I would like to go back to
Every
forces.
day, eat some Pop-Tarts and go home.
I'd like to go back to forces.
Back to back.
another
For AP Kim and.
Let's go back to the day that I missed.
What is
After
that
the day.
Temperature times mass over area.
Yeah, let's just do.
What is
It's Tesla meters per,
Oh, you're right.
no,
Okay.
that's not it. What is it?
So you have mu naught, which is known as the vacuum permeability constant. And it has these weird jacked up units, but now they will make sense to you. So if you have a wire, what this is giving you is the strength of the magnetic field around the wire. So you've got mu naught, 4 pi times 10 to the minus 7. But it has these weird jacked up units of Tesla meters per, is that area or do you think per amp? Per amp. Because,
I much prefer area.
sorry. So if you look at that, that's Tesla meters per amp. Now, that's a fixed value.
What?
You're gonna multiply that by current. Well, current's gonna be in
What is a
amps,
Tesla?
right?
Electric car.
Now, you have 2 pi r. Well, what, that 2 pi r is just what? Yeah, it's just the circumference. It's how far you are from the wire. Well, that's just gonna be measured in what? Meters. So the meters cancel out, the amps cancel out. The only thing you have left is Teslas. Okay? And that's what magnetic field is measured in. So clearly, and this is the relationship that we just saw. As the current gets bigger, what's going to happen to the strength of the magnetic field? It's going to get bigger. As the radius gets bigger, what's going to happen to the magnetic field? It's going to go down. And if you don't have a current, guess what? You don't have a magnetic field around it. Okay? So it makes sense. Now, if it gets a little, where it gets, there's a slightly different version of this. So if you look on your equation sheet, this is the second equation down. So magnetic fields is shown by the capital letter B, okay?
Which is,
I think the M's were all taken with mass. So, hey, don't kill the messenger, I'm just telling you. Shh,
I will commit a grave diplomatic insult.
don't. So, this is just this, so this equation is on your sheet. All this is that vacuum permeability constant times your current divided by 2 pi r. Now, if it is a ring, okay, like this, this is in your book, but it's not on the equation sheet. That gets a little bit weirder, but it's not bad. It's the same thing, but it's just, there's no pi, it's just 2r. So, the two equations are basically identical. The only difference is that if it is a straight wire, then you're talking about the circumference. If you're talking about a loop, then it's just the radius and how far you are. That is not the radius of the loop itself. It's how far you are from the loop. Okay? Huh?
The center of the loop.
No, it's how far you are from either side. Like typically it says, hey, what's the strength of the magnetic field 5 centimeters from the loop?
So from the center of the wire.
Yes, from the center of the wire. Okay, so here's one of the shorter assignments I will ever give you.
Please say it's just one question that we can answer verbally right
It's
now.
one
No,
question. A
it
to
isn't
double
that.
A.
Wait, what do you say?
Oh, with 27 parts. That
No,
take 2 hours each.
That each has 1, 2, and 3.
I will expect it to be turned in by tomorrow. It should normally take you a month.
Well.
Stop writing.
And 30?
Stop writing. No.
Nope, I'm in. I don't have any problems.
This is too long.
there.
Too many.
Too many questions.
I'm done.
Too many numbers. Get them away from me.
I get it.
Wait, guys, I can be happy.
This is how much it took me to do.
Exactly.
Yay.
So,
How many explanations do we have to get?
Probably a
Yeah,
lot.
please say it's not more than one. For the love of God.
stop. Well, leave it. Yeah.
Because I bet 20 guy and 30-year-old